Hi, my name is Chen and another group member is Chen Yining. Here I'm honored to introduce our topic, vector space and electromagnetism. Our content consists of 4 parts. The first part is simple introduction, and the second part is basic and critical application. The third part is modeling, and the fourth part is summary. Next, we will start our first part, the simple introduction.
Member Qi. Now let's introduce the first part, simple introduction. Vector and vector space. A vector space is a non-empty set V of objects called vectors. Vector is a quantity that possesses magnitude or length and direction, typically used to represent positions, movements, or forces in space. In linear algebra, vectors are often represented as ordered pairs or ordered arrays of numbers. Vectors can do operations such as addition, scalar multiplication, and they consist of vector space. Electromagnetism. Electromagnetism is an important branch of physics that studies the interaction and relationship between electric fields and magnetic fields generated by charges and currents. The theoretical framework of electromagnetism is composed of fundamental laws, notably the Maxwell's equations, which describe the behavior and propagation of electromagnetic fields. Electromagnetism finds wide applications in various fields, including electrical engineering, communication technology, electronics, astronomy, and even more. Now let's do the combination of that two parts. Linear algebra provides tools to describe and analyze complex physical phenomena, such as electromagnetic fields and wave propagation, and can also be used to analyze currents based on their linear structure. We will explore the theory of vector space and their applications in modern engineering and science, particularly in the modeling of electromagnetic waves. Now let's turn to the second part, applications. Let me introduce some simple applications, which are representing vectors for electric field intensity and magnetic field strength. Electromagnetic fields can be represented by vectors to represent their magnitude and direction, such as electric field intensity, which are called E, and magnetic induction intensity, which called B. And vector space provides you tools to analyze the superposition effect and propagation characteristics of these fields through linear transformation. For example, in the problem of electric field superposition, the composite field intensity of multiple points charges can be solved by vector addition. You can see the formula on the upper right side. A magnetic field calculation is also based on the superposition principle in vector space. Now, let me introduce the Maxwell equations, which is one of the critical applications, which are representing fields in electromagnetic waves in vector space. So we can use vectors to represent electric fields and magnetic fields, and use Maxwell's equations to describe electromagnetic waves. We can see the formula on the upper right side. Maxwell's equations are composed of several vector equations, so vector space can be also used instead of Maxwell's equations to describe electromagnetic waves. We can also see the equations on the lower side page. And then let me introduce the second part of critical applications, which name electromagnetic field and eigenvalue problems. Electromagnetic fields and eigenvalue problems are critical for understanding wave propagation and field distributions, especially in waveguides and resonant cavities. Maxwell's equations in this system can be simplified into eigenvalue problems. For example, waveguides. The modes of electromagnetic waves in waveguides are determined by solving the question as follows. Here k squared is the eigenvalue representing the frequency of the propagating mode. Resonant cavities. Field distributions and resonant frequencies are founded by solving these problems as follows, where omega is resonant frequency. And then to solve this problem numerically, continuous equations are discretized into matrix form, where A is the system matrix, lambda represent eigenvalues, for example, like resonant frequencies or propagation constants, and X represents eigenvectors, for example, like field distributions. This linear algebra-based approach enables efficient computation and analysis of electromagnetic system.
Next, we're going to build several models using the theory we mentioned earlier. The first model, with the above knowledge, we can model some simple electromagnetic scenarios. First, we analyze the composition of the situational field as needed, and then calculate the target result through vector space, as shown in the right-hand side. And for example, for the arrangement of the antenna array, we can use the vector space optimization method to consider parameters such as the position, shape, and orientation of the antenna to maximize the performance of the antenna. Represent the radiation pattern of the antenna as a vector and use optimization algorithm to adjust antenna parameters to achieve specific radiation pattern requirements. The picture above shows the effect before and after using the model to optimize the radiation weight. It can be seen that the optimized energy distribution is more reasonable and the propagation efficiency of electromagnetic waves is higher, which meets the needs of actual communication of radar. As you can see, the blue line is the model before using the model to optimize the radiation weight. And the red one, you can see the energy is more centering and is more gathering at the center in order to provide more efficiency in energy output. Next, the second model is data analysis and processing. And for signal processing and imaging technology in electromagnetics, by collecting and analyzing electromagnetic field data, such as signals captured by radar or sensors, vector space method can be used for signal processing, filtering, and feature extraction. These help improve the readability and utilization value of the data. Imaging and inversion technology. Using the theory of vector space, different imaging technologies can be developed, such as electromagnetic imaging or inversion technology. This method involves converting electromagnetic field data into spatial information to reconstruct the shape, location, or electromagnetic properties of the target. Next is the summary part. In summary, linear algebra plays a crucial role in describing and understanding electromagnetic phenomena. Its applications span across various aspects of electromagnetics, from field modeling to wave propagation analysis. The future of electromagnetic research is closely tied to advances in linear algebraic method. Continuous exploration and application of linear algebra tools can lead to innovative solutions and breakthroughs in understanding and manipulating electromagnetic phenomena. The existing 5G is already surprising enough. Who knows what kind of brightness the applied physics and electromagnetics of the future can bring? Thanks for listening. That's all.